My name's Jeff Houston. I work at APNIC. I kind of find it curious, and I'm not on the program committee. This is an operational talk. The performance talk is in tomorrow in the operational slot. So here you are in a performance slot, and this is actually a talk about operations. So with that aside, let's actually move this along a little bit. And let's talk about some assumptions that you make about the internet. A lot of what we think about the internet is based upon what the telephone system used to do. It was actually a tenet, a principle, almost a sacred belief of the telephone system that you could ring any number. There was nothing structurally blocking you, because in the telephone network, every single telephone number was reachable. And there are a whole bunch of international treaties and ITU regulations and all this kind of stuff that actually made sure that connectivity was universal. All telephones were equally reachable. Anyone could dial anyone else at any point in time. Is that true of the internet? Can anyone reach anyone? That's kind of an interesting question, and I'm sure most of you think it's true. You can send a packet to an address, and if the address is connected on the internet, you can get there, and they can get back to you. So that's what we assume, but that's not true. And you know it's not true, because almost all of you have firewalls out there. And the job of the firewall is to stop me from talking to you. So, in essence, most of the clients out there in a client-server architecture aren't reachable from the outside. You have to initiate the connection. I can't reach you unless you let me. So all of a sudden, this symmetric network has become asymmetric. So now the issue is, I can't reach anyone, but if I set up a public service on the outside of those firewalls, and I'm prepared to use port 80 or port 443, then maybe universal connectivity works for servers, right? And so the question is, even then, can you reach me? If I set up a server somewhere on the internet, can every single one of you talk to me if I want you to? Can you do that? Well, you might think that's true, but it's not. And I'm kind of interested in this question, how badly broken is the internet? Because I don't think everyone is connected to everyone else. It's not quite the case that connectivity is universal. So how do I measure this? Because I'm interested in trying to measure it. If you're lucky, you would have seen one of these ads. It comes up when you watch YouTube because Google do it. I place around 7 million a day. There's actually a heavy intensity of placement here in Sri Lanka. Google tend to place me in certain countries, and this is one of them. And you may have seen this ad. Now, what this ad does is almost nothing. It just displays upwards, thank you for helping us measure the internet. But behind it is a script. And what that script does is it pulls some URLs. And there's a list of URLs it actually tries to pull down. So the ad's displaying, and your browser is doing some fetches for me. So I'm looking at how well you can fetch those URLs. Now those URLs are very special. They all point at my servers. And my server is running a detailed packet capture. I can see every packet. And that's a snapshot of sort of all the recorded packet activity. We do around 7 million ads a day. That's how many ads we do a day. Google are very good. Don't click, by the way. Don't click on the ad. If you click, I pay. As long as you don't click, it's free for everyone. It's an amazing system. Love ads. Ads are good for us all. So it's an ad-based measurement network running at about 7 million ads a day. What if you can't reach me? Now, maybe it's that I can't reach you, because it's kind of the same problem in reverse. And I see a lot of this. When you look at how the underlying protocols work, the fetch is a fetch using TCP. And it doesn't matter if it's port 443 or port 80. It doesn't matter if it's encrypted at this point. The initial handshake is in the clear. When you, the client, want to talk to me, the server, you send me a SYN, I send you an acknowledgement, SYN-ACK, you send me an ACK, we're connected. And I'm interested in that small set of folk that don't complete the handshake. Here's the V6 failure rate. And around 2% of connections in V6 don't complete. 1 in 50. Consistent across months. Now, it was worse when you're running Teredo, it's worse when you run 6 to 4, it's worse when you do tunnelling. Tunnelling is an invention of the devil, don't do it. But even without tunnelling, V6 is still shockingly unreliable. It just doesn't work very well. Now, I'm interested as to why that breakage is happening. 1.5% failure is a shocking service, and that's the service we're running in V6. You can't run a service with 1.5% of connection failure. So I kind of think, well, what's going on? Is it lousy consumer premises equipment? Is it some kind of tunnelling problem, strange firewall filters? And then you think, is this only V6? Can I see the same failure rate in V4? And the answer is you can. That consistently the V4 network doesn't work rock solid. The failure rate's around 1 in 500. 0.2% of all connections coming out of this ad don't complete. They just hang. Now, it's not auto-tunnelling. It's not V6 lunacy, and there's a lot of V6 lunacy out there. It's not lousy CPEs. It's not untried, sort of slightly flaky V6 software running here. This is V4. We've been doing it for decades. So why is there failure in V4 as much as there's failure in V6? Is it asymmetric connectivity? That's an interesting question. And so there are a number of points where you get to see all of the internet all at once. And that's not easy. But if you run a BGP routing table and you take a full feed, that feed is all of the internet all at once. And so a BGP feed is the internet. Now, there are a number of places around the world, and the Route Views project at the University of Oregon is one of these, which doesn't collect just one BGP feed, it collects about 50 all at once. And what I do is I've deconstructed it and plotted each of the individual peers over time. And what you see is the route table has grown since, 1980 mumble up to today, and it's now approximately 660,000 entries from 50 different feeds. But look at that. It's not one line. Let's blow it up a little bit. That's just the last few months. It's not one line. Every single peer of route views has a different collection of routes in total. 75,000 routes are the span of difference. So all of these peers of route views aren't sending the same default collection. Each of them have a subtly different view of what they think the entire internet is. Gee, which one's right? Is more routes better than less routes? Who's got the best view here? Because what is really obvious is they don't have the same view. I also added to this picture, just to make it even bigger in terms of difference, our colleagues at the RIPE NCC also run their routing information service, and they have a very similar thing to route views. So I added all of their routes as well, just because I had a computer and I could. So what's going on? Is this traffic engineering, or is there true reachability difference? So the next thing I did is, instead of counting the number of routes, I count the span of addresses. Because even if you take more routes to do it, if we agree about what we see in the routing system, it should be the same number of addresses, shouldn't it? And it's not. Again, if you blow it up, what you actually see is that across all these peers, there's the equivalent of a /8. 15 million addresses that some folks see and others don't. It's not just one /8. All these little things are spread all over the entire address space, but it's different. Not everyone sees everyone else. So what we're seeing is everyone's saying, I have default, but default changes. Everyone has a different view. Now, is this just less than that. So now individual peer networks will see some routes that are in the default set, some routes that aren't, and we'll be missing some as well. So now I'm looking at the variance from default. And every single peer has some more and some less than the default set. And it's steady over time. So this isn't a routing protocol issue. This is the way you peer and the way you purchase transit has different results for different players. Crossfolk as to what default means. And you can actually start to list each individual peer and see, well, who's advertising more than default? Who's got more and who's got less? Who's actually working with a subset? I won't go through them. You can read it online somewhere, but there's a list of folk. It's probably clearer on your laptop than up here anyway. And it actually looks at each of these players to see where they sit with respect to default. That's in RIS in Europe, exactly the same issue. The top one up there, AS, what is it, 39,989? It's missing an entire 39 million addresses. Just can't reach them. And you sort of go, but isn't that curious? That we're getting so many problems in what default is across the entire network. Not everyone agrees with everyone else. This is V6. Up there, for example, is Hurricane Electric. It's missing 19 million /48s, and it's got an extra 19 million that are different. It's just default seems to differ from network provider to network provider. Same with RIS. So this leads to a number of conclusions. There is no default. There's no time where you know as an ISP you've got all the routes you should have, because we don't understand what all the routes you should have actually is. And it's stable. You're not trying to do a better job. You're not doing a worse job. It's just stable. Our assumption that tier ones offer default and universal connectivity is a broken assumption. That's not the case. What they offer is a subset of that. And all their resellers offer subsets. And the other thing I found too, which I find fascinating, and here's Sprint, AS, is it 2914? Is that either Sprint or NTT? Sorry, thanks, Philip. In America, 2,808,000,000 addresses announced to route views. Thank you, NTT. In RIS in Europe, the same network, AS2914, offers 2,807,000,000 addresses. What's so special about that other million that they're kind of not in Europe but only in America? What's going on that even NTT internally doesn't understand what default is? Why do we do this? Now, so what? Default's different. Now, there was a paper out, and I don't know what happened to the graphic. Oh, here's the graphic. There was a paper out, Randy Bush actually presented, I think in APNIC a few times, about the fact that folk tend to follow an invisible default route even if they don't have all the routes, which is fine if you're Facebook, which is fine if you're LinkedIn, which is fine if you're Google. It's fine if you sit in a tier one network because everyone can reach you if you're in a tier one network, because that's what default is all about. But if you sit on the leaf, if your server is with my server back in the dim, dark, stringy bits of the internet, default doesn't work anymore. You need specific routes. And that's when you have reachability problems. So I get this connectivity failure in V4, and the real question is what's causing that connectivity failure? And I think part of this is structural. Part of this is the fact that some parts of the internet don't see me. Can I test that theory? Well, interestingly, when the return path is broken, sometimes I'll get back an ICMP saying, tough luck, the destination is unreachable. I do not have a route. And so what I should see is an incoming SYN, and then an ICMP destination unreachable for my SYN-ACK. And guess what? I see them. So what I see in my packet traces is precisely that my effort to respond generates a reachability failure. You can't get there from here. And some routers, sometime, send me back a diagnostic going, tough luck, you've run out of routing. it just isn't going to go there. And the payload is my original SYNAC. And I get a fair few of those, so there is some certain element of just connectivity failure happening on today's internet. Of course, don't forget, firewalls and various other forms of NATs are also massive ICMP generators, and destination unreachable doesn't always work. The more NATs you deploy, the more you see this kind of failure. I don't know if anyone's been looking, but what it's saying is you can't reach me when I'm the source address in both cases. In other words, what's going on here is you can't reach 197.114.30. something from 197.114.30. something, which is a strange packet unless you figure out that that's a CGN, and CGNs, when they break their binding, basically give you back ICMPs for free. So what can I say? Well, connectivity isn't what you think it is. And that as ISPs, you're doing an average job about reachability. It's not very good. And there's an awful lot of gaps in what you think is default. Now, some of it is this asymmetric. Other parts of this are just aggressive NAT behaviour and other bits of brokenness, and we can't tell what happens to the rest of us. But what you can say is that it's not the case that there's connectivity that's universal in the internet. That connectivity is a little bit more accidental than that. And that while most folk can reach most addresses most of the time, that's not true for everyone all of the time. It's kind of almost anyone can reach almost anyone else, well, most of the time, if you're lucky. So why don't we care? Why isn't your help desk exploding? Why don't people say, I can't reach X, I can't reach Y? Because you don't use the network that way anymore. This is not the network we run today. To be brutally honest, what we run is a Facebook feeder network. And as long as all your customers can reach Facebook, Google, Netflix and eBay and Amazon, no one cares. Absolutely nobody cares. So what we have right now is not a universal connectivity network, we have a tier 1 feeder system. Now think about that a little bit. And you might say, well, that's really bad. And it does kind of make me sad that we've destroyed universal connectivity. On the other hand, what if we went all the way? And what if the only routes we had in our network were how to reach Google, how to reach Facebook, and how to reach Yahoo, right? How could you ever mount a DDoS attack on anyone other than Google and Yahoo and so on? You couldn't. So if you're really concerned about security and reachability, if you're really concerned about DDoS attacks, attacking random folk, then maybe we should just give in. Maybe we should say back to these folk, it's your internet, we're sorry to have mucked it around. What we're only going to do is to carry 4 routes. Routes to each of the big content providers, and the rest, nah, you just can't get there from here. Thank you very much.
If you have any question, you can ask. Okay, no question. Okay, Anurag.
Sorry, stand up. 20 minutes here, front time.
Hi.
Hi.
Anurag from Hurricane Electric. I have a question for you. I think slides were primarily, the data was primarily based on routes which you are learning, not exactly how efficient those routes are. So my question is, in many cases, we will see that routes are there, but they are heavily inefficient. Have you done any study specifically about tier 1s in that respect? Like tier 1s not announcing their domestic routes in certain region to certain other selective tier 1s?
What you're talking about is some degree of traffic engineering as distinct from reachability. And what I was trying to do was to eliminate explicit routes designed to do customized traffic flows and eliminate that from the idea and sort of look at raw reachability.
Okay.
So in terms of doing the comparison of those routing sets, the tool that I used took out all the more specifics.
Yes.
And we're left with, if you will, the upper reachability set of addresses and compared them as reachability. So it's a subtly different kind of question to reachability plus engineering, which is what you see in a normal BGP feed.
Sure, sure.
Now, as to how far could you take this and where could you take it, there is a real problem with any kind of measurement on the internet. And the problem comes from ISPs. You think it's your data, and you think your data is private and you're not willing to share it. I think it's a public network and you're being precious. And you're making the job really hard for all the rest of us to actually understand what's going on and how to make life better for you as well as everyone else. And as long as operational data remains a tightly driven secret, for the measurement community, we're sitting on the outside scratching our heads guessing. And this is kind of the best insight we have in the absence of real data.
Right.
And that's frustrating at times. So yes, there probably are better answers, but we're not allowed to see them.
Yeah, I think having a source of looking at table from that design, it would be very, very useful to see what kind of announcements do ISPs do in, say, Europe, in US, in Asia to each other when they actually peer with each other.
A fine piece of study, beautifully, the RIS and route views data is public.
Yeah.
You can do it too.
Yeah.
So I encourage you to study it too.
But not the selective ones, because it's still dumping off the whole table.
Totally.
Yeah. Thank you.
Thank you.
Okay, I'm Gihandas from Sri Lanka. So I was sort of looking at, I think pretty much one before your last slide, where you said almost everyone can reach almost everyone almost all the time. I thought that was pretty good. Then, I mean, obviously we cannot expect 100%.
The telephone network did it. Why is it impossible for us? Why, when we were running a telephone network for 80 years, we actually managed, when we introduced international dialing, to do comprehensive connectivity as an inbuilt engineering artifact. It's not hard, we just don't want to do it. And that's the challenge I put to you, that if you kind of go, well, that's okay, you're compromising on second best.
Right, so let me continue. So, yeah, so 100% is always hard. For example, if you're looking at reliability, I mean, no one can have 100%. We are looking for 99 point whatever. So I'm just trying to figure out what, if you try to enumerate those all modes, what are we looking at? 99%, 99.9%, what are we looking at?
What we're looking at currently is 15 million addresses that vary across most of the large-scale providers across a total of 1.2 billion addresses. If one of those 15 million is you have a problem. So statistically, you kind of go, it's nothing. But if I'm one of them, I feel the pain, and you're feeling the pain. And to my mind, it's second best. It's not what we should be aspiring to. It's not what we should be doing. But somehow, we just don't seem to have the tools, the techniques, or the desire to actually make sure that default really is default, that all of the routes are accessible to all of the internet all of the time. We're just failing in that last little bit. Thank you.
Thank you, Jeff. Okay, I'm requesting Monica from Cold Technology. Please come here and present your presentation on the title, Enhancing Service Provider Network Efficiency. Please come here.
Good afternoon, everyone. I'm going to be presenting on enhancing service provider network efficiency. So what is network efficiency? It's basically ways where you can improve or you can increase your revenue, your return on investment, your profit margins. And how do you do that? By reducing your CapEx and OpEx and increasing your scalable and flexible networks, which can meet the customer growth. There are many parameters that really influence network efficiencies, but I'm going to be discussing only a few of them today. Those are simplification, automation, virtualization, programmability, and innovation. Just taking just look at our historic network architecture, a few years back. We had two parallel networks, one for Ethernet and one for data, the IP. Now, most of you, from the operational background would really understand the pain of maintaining two networks. It's not just about rack space, power, but maintaining two different hardware, which means you have to actually go through the hardware and the software life cycle of the follow-up with different vendors, and at times also have different operational excellence, which is very difficult to maintain. Simplification in this case would definitely help, and how do you achieve that? Integration. But I wish it was as simple as a click of this mouse and we could just reach the targeted network architecture, but it's not. We have a lot of challenges when we're trying to achieve this integration. I'm going to be discussing specifically on the CPE layer. Looking at that use case, where we had multiple CPEs, you had a L2 CPE connected to L3 CPE where you would be really giving services, yeah? So that's a traditional way of delivering your VPN or internet access connectivity. What we have decided is we would move this network function onto the PE, yeah, that's the hardware-based PE, and move the entire network function over there. But what it meant was, of course, few challenges, one of them being monitoring. So initially, our L3 CPE was the monitoring point, but when we moved this functionality onto the PE, then of course our monitoring point also moved to the it just shifted to the L2 CPE. What it meant is, of course, we needed to adapt to the new protocols like the connectivity check capability, the CCMs, right? And we were also dependent on the vendors to really have the TLV-based implementation in order to achieve monitoring. QoS was another good example. Initially we did all our classification, marking, scheduling, shaping on the L3 CPE. Then, of course, when the L3 CPE, the functionality moved on to the PE, then the entire QoS moved on to the L2 CPE, which meant instead of the IP class or using the HCP, which would give us 64 classes, we were now limited to the .1p bits, which were limited to 8 classes of service. So there were multiple challenges we spoke about. I mean, of course, few more. The additional, we would need licenses for some of the niche features like NAT and firewall if we had to do it on the PE. There was no really resource level segregation in the hardware. They were all VRF-based deployments. Now again, because we were loading our PE with more and more features, scalability was becoming a concern and becoming more and more difficult to measure. There were no uniform capabilities across different vendor platforms. It varied from one to another. We already saw the restriction on the QoS capabilities. Also, since our L3 functionality moved into the PE, L3 encryption was no more available with this kind of VCP implementation. So what next? I mean, we just took the logical step. I mean, we might not have answers to all the challenges, but some of them, yes, it was the most logical step to move towards NFV, which would improve the network efficiencies, yeah, by moving the network intelligence and functions to the software-based deployment on the generalized COTS hardware. We would get the network scalability and elasticity. It could mean we could cater to the on-demand traffic requirements. We could handle the traffic spikes much better. We could have the agile and the flexible service. We could really cater to the on-demand capabilities. Automation, unit cost reduction, and of course the innovation improvement. And we could really, have faster time to market, so we could deliver a service quicker. So just looking at probably the initial thing when we said, right, the traditional way L3CP, where we had the L3CPE, the hardware-based model, then we moved on to the hardware PE-based VCP implementation. And now we're talking about using the leveraging the NFV architecture and doing the VCPs on the NFVI. It could also mean we could do the distributed NFV architecture, and we could really have the COTS hardware deployed as the CPE edge to deliver similar functionality. Now just let's look at some of the design considerations that we really had to do when we moved on to the NFV architecture. The VNF, so you actually, when you're deciding that, so the elasticity, whether, how good your VNF can really scale up or scale out. Multi-tenancy becomes important because it's a way you could make your system more cost efficient and resource efficient, because now you would be having multiple tenants on the same VM or VNF, right? However, that means your segregation of traffic between tenants become more and more important. Service chaining, how good, if you had different network functions, how are you going to stitch them together? Since it's a software-based implementation, your licensing model becomes very, very important, especially when you're trying to do cost modeling. Your feature capability, which is existing, and of course the adaptability to latest technology development, how soon a new feature that you need can be made available. Your interrupt with other components, your release management lifecycle, and of course the support model. So what are the considerations you need to do for the NFV infrastructure layer, or the NFVI? Whether you want to keep it centralized or distributed. Now that would depend, of course, on your network function use case. Whether you want to put it on the node or the CPE edge, that would be governed by the function that you are trying to implement. Whether it should be a bare metal or a hypervisor, well again, depending on your network function. You would typically use bare metal if you had to deploy it on the CPE edge and hypervisor on the node, because you would be doing multiple VNFs over there, and you want to aggregate your resources. Of course, when you talk about hypervisor, next question comes in, whether we should go, which kind of virtualization layer should you go with? Should it be SXI, or should it be KVM, or Zen, or anything else? Of course, the question is, it's more what you're comfortable with, but of course, KVM is is open source, and I think there's more development on OPNFV, so, KVM should be the most likely choice. With all this infrastructure, it becomes more and more important that you have a management solution. Now, whether you try to do it manually or using OpenStack or a third-party integrator, how do you make that decision? Of course, for the smaller deployments, due to the low implementation effort, manual management is something most likely just to see how it goes, but it's just a short-term solution. For a long-term solution, you would have to look for a management solution, which could be an OpenStack management or even your third-party integrator. So let's look at the some of the bottlenecks, performance bottlenecks that we face. Typically, a network equipment can handle around 14.88 million packets per second. But your server in the data center, it's only equipped to do 1.2 million packets per second. So of course, there's going to be a lot of packet drops. But that's not just the end of it. When you do a network equipment, it's easier for you to troubleshoot. If you're getting packet loss, you know which vendor to follow up and where exactly it's dropping. But now you've got like 4 different points. There are different interfaces. There's this driver level, there's a virtual switch, and there are a whole lot of communications between your host and guest OS, and of course your VNF, the application, the virtual appliance, where exactly you've got to nail it down where the packet loss is happening, right? And of course, and then your performance enhancements would then come into picture. So of course, some of the way to optimize server performance is, of course, you need to definitely have a carrier-grade performance. Some of the ways you could achieve is using SRIOV, where you would be bypassing the hypervisor virtual switch, and you'd get optimal performance. But of course, it comes with a price. So there is issues with portability, flexibility, and complex traffic steering. So you would lose all the benefits you would get out of the virtualization layer and the resource aggregation. You could use DPDK, which is a set of libraries which is presented at the user host level. But again, it's a vendor-based deployments, which can achieve around 5 to 8 times, but you're dependent on their way of implementation. There's no standardized way of vendor implementation today. Blind rate, it still cannot be achieved, for using DPDK. So this is some of the results which might not be visible, but if you actually look at, it's 2,000 flows for IMAX packet size, we could only get around 2.5 gig. And then as you increase the number of flows, this actually further reduced to around 1.4 gig. So that's just to emphasize the impact. Now, of course, as I said, you cannot solve all the problems, but then, getting from all the, benefits, software-defined WAN, which basically leverages your SDN and NFV. So it is nothing but it's an innovative way of providing transport-independent VPN overlay over any kind of IP connectivity. So the customers can actually quickly connect, to their VPN at low cost. There is zero-touch provisioning, so it's basically a play and plug deployment model. Also, there is traffic steering that is available depending on your traffic profiles, also dependent on your performance. So if the performance in the network degrades, you could actually steer the traffic on the backup path. So you could do a lot of things, offload traffic, again, depending on your business requirements onto different paths, and leverage this whole new development. So what are the benefits and achievement? Of course, you got to reduce cost. Yeah, this is typically what we've achieved at Colt. Yeah, there's better orchestration with so much of programmability and virtualization. There's a faster service delivery, the faster time to market. You could get your solution quickly to the market, and it's all simplified. So what's the journey so far? We simplified our network, which meant we do a network layer integration, which allowed us to do virtualization. Initially, we did it on the hardware PE router based, and then we explored and evaluated the NFV-based deployment, which allowed us to do further innovation in terms of programming our network, to leverage SDN and NFV, and provide SD-WAN, which is a transport-independent WAN, all using the zero-touch provisioning. Thank you. Questions?
Do you have any questions? No? Okay, thank you so much, Monica. That was an excellent presentation. Okay,
Our voices are so recorded.
now we have comes from Akamai Technology, and he's going to present the presentation on CDN and internet traffic analysis.
Thank you. Hello, everyone. So, my name is Kim Xiong. I'm one of the network architect of Akamai. So today I'm going to talk about some very basic about CDN, especially from Akamai's perspective, how Akamai CDN works. I think most of the ISP, telco, carrier, they always have this kind of question. I'm going to share some results that we just released 3 days ago about the internet traffic trends that we observe. So I think I skip most of this. So basically, Akamai is not only a CDN player, but we also do security and we also do application acceleration. So we are one of the largest distributed platform for doing the CDN and other services. So we have more than 200,000 servers in more than 2,000 locations and more than 120 countries that we have. And day to day, we are delivering over like 2 to 3 trillions of requests, and we are serving like 40 terabit of traffic. So it's usually like consists of about 15 to 30% of the internet web traffic that we are delivering. Yeah, so CDN. So a lot of people, CDN is traffic definitely increasing. There's a lot of different CDN. So the way that we do, so there's a lot of different CDN. So some are like cache server, some like Akamai, we do DNS based, and some others do Anycast. So there are different type of CDN, but in general, CDNs mean we want to direct the user to the closest server, and then we deliver the content from that server, because that's the shortest latency, highest throughput, so the better web experience for the end user. So the way that we map the end user to the CDN node, this is called mapping. So either DNS or Anycast. So Anycast, I think you guys pretty much familiar with, because Anycast is basically based on BGP. So it allows to send prefix set to everywhere from the CDN node, and then depend on BGP to see which path is the closest path. But in Akamai, we do it differently. We do it based on DNS. So what it means is we will map the end user to the closest CDN node based on the user DNS server. So just take a very simple example. So let's say if you want to go to Akamai's website, so this is a real example. So if you look it up from Sri Lanka here, using a Sri Lanka ISP DNS, we'll give you a Sri Lanka server IP address. But you are in Singapore, then using a Singapore ISP DNS, then we will redirect you to the Singapore servers. So basically, we hand out different IP address based on the DNS IP address. Of course, the logic is not that simple. So other than the DNS IP, we also measure a lot of things. So we measure from the Akamai CDN node to the end user. Is it based on the latency, based on the throughput, packet loss? Basically, we measure the network performance from our CDN node to the end user, and then to see at that time what is the best optimal server to deliver the content. Of course, it also depends on our CPU, hard disk, and the network utilization also. So this is a simplified version of how do we map the user to the closest node. So you can see there's a few steps here. Oops, sorry. So the number one is the end user will send a request, usually a web request, HTTP request, to ask where's the IP address of the web server. So step one here is, okay, this here is example.com. So they look up, hey, I want to browse example.com. So where is go? So you ask the ISP DNS, hey, where's example.com? So ISP DNS will go through a recursive lookup, a literal lookup, go to the root server, the .com, the customer, content customer example.com DNS server, and then from there they CNAME it to Akamai. So in this example, the DNS server that who hosts example.com is CNAME to a212.g.akamai.net. And then from there, because it becomes an akamai.net host name, then repeat the same thing, but just now we're doing the recursive lookup to using Akamai DNS server. So when you request from the Akamai name server in step 3 here, when you go to the Akamai name server, we know where's the DNS query from. So we know the ISP DNS IP address. And then from there, we talk to our mapping system, hey, where at that time was the best cluster, best Akamai node to serve requests from this DNS server. So we think, okay, this guy is actually from DNS server 1, 2, 3, 4, and they are requesting for resources that we call a212.g. Okay, at that time, okay, we said, okay, we have available resources on the local cluster in the ISP, so we redirect them, hey, please go to 5, 6, 7, 8. So the DNS answer, we go back to the ISP DNS, say, hey, please direct the user to 5, 6, 7, 8. So then the user, at the final step, the user in step 6 here, they will go to the closest Akamai server and then deliver the content from there. So it's go through a step of a recursive lookup, and then our Akamai name server will think about, talk to the mapping system, hey, at that time, what the server is the best to serve the end user. So this is the overview of how do we do that. So we actually highly rely on the user DNS. So we do some statistics here that we are in Sri Lanka. So we do, this is like, I think the data that I do 2 weeks ago. So this is different AS in Sri Lanka. So what we're trying to, we collect data, so we see, okay, the user in, let's say, different AS in Sri Lanka, what DNS the end user are using. So you find that, okay, sorry, I can't disclose the name here, but let's say there you see that quite some few of ISP users, they're actually not using their own ISP DNS. they are using Google. And you can see that it's quite high percentage, it's like 22, 35, 15% of user that using Google. So it could be either the end user, they hard code the Google DNS on their machine, or the ISP actually redirect for the QE to Google, or their infrastructure, they don't have DNS infrastructure, they just, on their DHCP, they just hand out Google DNS, which I don't know. And the other interesting figure is like on ASC, this is another, an ISP also in Sri Lanka, they are using like almost 29, almost 30% of their DNS QE, the user are actually not using their own DNS, not the ISP DNS, not using Google, not OpenDNS, they're actually using some others. Yeah. So this is, you can see that is quite interesting example that if the user using Google, that's fine actually, because we do have EDNS mapping with the Google and OpenDNS. So we still, our mapping system could still map the user to the closest node. But if you are using other ISP or using something else, then our mapping system will not be able to map to the optimal node. So hopefully this is a high-level view of how CDN works. And next, I'm going to share some data that we just published on Akamai. We call it the State of the Internet report. Yeah, so as we said before, Akamai, we have over 200,000 of servers. So we actually, day to day, we collect a lot of different requests. And then from there, we collect all the HTTP log, and then we can analyze those big data, and then we create this report to share with the community. So you can actually download it, but I'll just extract some data that is more relevant based on the Asia, the data, the ISP in Asia, the countries in Asia, and also highlight the data for Sri Lanka. So so this data, all data that hitting Akamai servers. So some of the highlight from the report that we have. So we saw a global average connection speed actually decrease a little bit, decreased 2.3% compared to last quarter. So we do this report per quarter, and this decrease, but the FH, I think this FH peak connection actually increased 40%. That's right. The global average connection actually increased. The decrease per quarter, but actually increased year over year. The average peak connection is increasing to 3.7% to 36, and year over year we see that this 2.5% increase. So the internet itself is actually keep increasing, the FH speed, and then we also see a lot the broadband adoption rate for 10 meg is going 0.7% quarter over quarter, and the high speed one, the 15 and 25 meg, is also increasing a little bit, 0.8% and 2.1%. So these are the data that we measure because, for example, if you have to do a 4K streaming, then you need a 50 meg connection. So that's why we are saying that 10 meg, 50 meg, and 25 meg is quite critical. If you have a high broadband penetration rate of 50 meg, then you are actually ready to do 4K streaming. Some other data that we observe is on V4 and V6 data. So the number of unique IP address that we saw is 800 million. It's actually less than the total internet population because some ISP, they do NAT, or the IP address could be reused in a broadband network, for example. For IPv6, we saw that Belgium is the global leader for IPv6 adoption, is 38%. It's actually Belgium is the top from our Akamai perspective for several quarters already. It's still going up. And for other providers, we saw that like Cable Wireless, Verizon, T-Mobile, Sky Broadband in UK, they all have a very high percentage of traffic that they request is prefer V6 over V4. So you can see that like Verizon, they are actually 74%, which is very high percentage. Yeah, and for mobile connection, so we also, because we know the network agent, the end user, there could be from a mobile agent or from a mobile network, so we can also measure the mobile connection. So the FH connection is quite vary from 23 meg in UK and could be also 2.2 meg in Latin America. But we see that this is also, the mobile connection is also going up because of a lot of countries, they roll out 4G, and some countries, they even roll out the, here I read the news that Dialog here in Sri Lanka, they also have do a network deployment with LTE, advanced version, they can do 1 gig connection. So you can see that the mobile connection is actually gradually, the more users going up, and also the mobile connection speed is sooner or later with LTE or with 5G is going to be going up even higher. So this down to, then this the data down to per country that you can compare the FH connection speed. So FH connection speed, so FH peak connection mean, so we get all the connection, we down from the HTTP log, we know how long the user download the data, so we know the connection speed, and then we find the peak, and then, but we FH out. So we have a peak daily, and then we calculate all the FH, so it's called FH peak. And Sri Lanka here, they actually ranking like globally number 63 in terms of the FH peak. It's actually still quarter and quarter and year, it's actually keep growing quite substantial from. So you can see the growth rate. Sri Lanka actually grow fastest compared to other like developed countries like Singapore, top but countries. And this is a historical trend of the traffic in Sri Lanka. So this is the FH data that we see. We collected, this data is starting from Q3 2002, so Q3 2007. So at that time, the peak connection is about 2.5. But I can see gradually up to, I think, like 2014, the connection actually start increasing rapidly. And then so recently, the FH connection is 43.9 for Sri Lanka. FH connection, again, Sri Lanka is about like 80%, and but number 11 is increasing like 5.6% and 20% on quarter-on-quarter and year-over-year. And this is a similar, I think this is the FH connection speed trend that we observe. It's also similar to the FH peak connection. So this is, you can see that starting from like Q2013, 2014, the connection actually jump up quite rapidly. So I think the ISP here, they do a great job to make a better internet for the end user. So the FH connection now is, within 10 years, they actually go up quite rapidly. Now it's 5.7. And this is the adoption rate that we observe. I don't go into like details, but you can see that Sri Lanka is, I would say, it's not as good as the developed countries, but you can see that it's actually not quite good. It's actually over even higher than Australia and Malaysia. And this is the format adoption rate. Again, like starting from Q1 2013, we see a dramatic trend. And now over 83% of the Sri Lanka user, they got at least 4 meg connection. And 10 meg connection speed is actually similar to the 4 meg. It's not that, for 10 meg, it's actually not, the penetration is not that high yet. It's talking about like 6.2%, but you can see that the graph is not showing very good here, but you can see that you can see a linear growth on the 10 meg adoption rate. And finally, this is the 15 meg adoption rate. Because it's not that exciting, but again, if you look at like zoom into the data, it's actually going from almost none 10 years ago to now starting up to 1.6%, and it's like an exponential growth. So we are, hopefully next year you have higher percentage of the broadband adoption. And this is just a comparison chart of number of unique IP address that we saw in different countries. China being the largest population and the largest internet users, then you see over 124 million of unique IP addresses that we saw from China. And Australia, I think, is the, also in Australia, like Taiwan, I think the second, also Japan is the Japan, yeah, this is second largest number of, in terms of number of unique IP address. Sri Lanka, we only observe like 160,000, which I think is lower than the internet population. And a comparison of the average connection speed among different countries. Yeah, and then some data on IPv6. So sorry the graph is so small, but basically I just want to highlight that we are seeing that a lot of more and more ISP, they start to adopt V6. So as of May, Akamai, we have deployed V6 in over 100 countries, over 700 network providers. And this is the in terms of IPv6 traffic that we observe. I just highlight the one in Asia. So in Asia, we see Japan and Australia, they have the highest percentage of V6 traffic from Akamai. And this is just a top 10 traffic in terms of country that, unfortunately, we don't have any Asia country here. But out of the top 10, Malaysia and Japan is the highest. And this is the IPv6 adoption in Sri Lanka. So I just calculate this, I'll just get it from this year. So it's starting from January 1st of this year. And gradually we see that the V6 adoption in Sri Lanka is also increasing. It's not that fast, but I think it's getting there. The adoption rate now is talking about like 0.8%. Yeah, so this is the data that I want to share today. And just follow some conclusion that, so Akamai is one of the largest CDN we based on DNS mapping. In Sri Lanka, we saw there's a lot of users that are using a third-party DNS. Doesn't necessarily be bad, but this is the observation fact that we observe. And share some data on the V4 and V6. So I think definitely V6 is going globally. So if you don't have V6 deployed in your network, start to think about that. Yet if you have an Akamai server and you don't enable V6 with us yet, talk to me. Yep, so that's the presentation that I have. Thank you.
Thank you so much. Okay, we have a question.
Two questions. Yep. Thank you. Number one, the averages you're citing, are they median or mean averages?
The average mean we collect all the HTTP log line, and then from HTTP log line, because we have the start time and the end time and the payload. So from the time window and from the payload, we can calculate the average speed. So we actually basically we collect every log line and we calculate. So this is a average.
Okay, but is it a median average or a mean average? Are we seeing that half of the connections are faster and half are lower as a median, or are we seeing that 10 people had a 1 megabit and one person had a 10 megabit, and thus the average is 3 megabits?
So it's basically just average.
Yeah, mean average, okay.
Yeah, mean average.
Number two, you said there were only 160,000 unique IP addresses in Sri Lanka?
Yep.
Do you have a way of seeing individual PCs? Do you have some marker, some cookie, some way of determining how many devices? Because it's obvious there must be carrier grade NAT involved there, because there's so many more than 160,000 internet users here.
Yep. So the way that we do is so again, this is all from the HTTP log. So we see the end user, the IP address, and then we just calculate how many are unique IP address. So unique doesn't mean they are one single user. So it could be, let's say, a broadband user, they assign this IP address to user A, and then the next day they assign this IP address to user B. So you just calculate based on unique IP address. And of course, NAT is also one of the major factors that let's say, enterprise or maybe an ISP, they assign private IP address, and then publicly they allow, we only see one public unique IP, we only see one public address. So these are the two major factors that we see. Yeah.
Okay, thank you.
No problem.
Hi, Anurag from Hurricane Electric.
Yep.
Cam, broadly, it seems like there are 3 categories of DNS servers end users could be using when they are hitting Akamai-based strings. Either they are using their ISP's DNS server, which is announced to you in the passive BGP session on the Akamai cache, or they might be using popular DNS server like Google's 8888 or OpenDNS. I think in both of these cases, the mapping works pretty well. But for the third case, which you also mentioned, for anyone using any other DNS server, the mapping is usually not very optimum. One fix which was suggested long back was of the eDNS, of including client subnet in the eDNS request. It seems like Akamai has a deployment of that with Google, with OpenDNS, but not with all possible, any random DNS server. Is there a reason why it's not deployed as yet?
Yeah, so I think this is 2 things. One is not many ISP, they support eDNS 0. The second thing is there is a internal process to enable. So we are not limited to only Google and OpenDNS. Definitely, if you are let's say you have an ISP in Indonesia, for example, and you have central DNS in Jakarta, and but you have user in Surabaya or Bali, then if you support eDNS, definitely we can discuss about how we can map your user better. So this is something that we are open discussion with any ISP that support eDNS 0. But just we are not observing a lot of ISP, they actually support eDNS 0.
Okay, I mean, it seems like more of chicken egg game, but you are in a better position to break that, isn't it?
We do actually, I can't tell the exact name, but we do have 2 or 3 carriers that we are discussing about eDNS 0. Yeah, but we just need to make sure that there are we actually whitelist them correctly, and then we understand the end user information.
Okay.
Is that okay?
Yeah, sounds good.
Yep.
Thanks.
Hey.
Lohan from LaRousse Cloud Service. I have a question regarding the total amount of unique IP addresses. I've been following Akamai State of the Internet reports for some time, and it seems this is one of the very first times that actually the global IPv4 unique IPv4 count actually declining. The US was seeing declining for quite a few quarters already, but in terms of the global amount of addresses, actually quite one first time actually seeing it's actually declining. Do you have explanation to that? And is that like really the first that we're seeing the declining of V4?
Yeah, I think it's actually depend quite country by countries. Actually in Sri Lanka, I don't have the historical data so here, but if you look at the historical data, the Sri Lanka actually have, I don't know, let's say 250,000 of unique IP address since 2 years ago, and then it's actually gradually dropping down. So I don't have the exact correct explanation for you, but this is what we observe. So US, we are observing a decrease, but the other thing is like US is because this is unique V4 address. So a lot of users, they shift to V6, then we don't see the V4 address again. So like the US, a lot of mobile operators, they aggressively deploy V6. So the traffic end-to-end will be V6 between the user to Akamai. Then we don't see any V4 address from their user. So in US, we saw a decline because of the mobile operator, they deploy more V6.
Okay, thank you.
Hey, hi Josh.
Jeff Houston, I just wanted to correct some of this conversation about eDNS 0 client subnet use, because I think you've got it sort of backwards. The issue is that recursive resolvers have the option of presenting the client subnet to the authoritative name server. And in general, they don't. Now, it used to be a magic whitelist. And if you contacted the secret cabal, your server could be listed on the whitelist, and the recursive resolvers, notably Google's, would then add eDNS 0 client subnet to their queries to you, and then you, the authoritative name server, could give back basically a relative answer based on some supposed guess about the client subnet.
Yep.
Google stopped doing that many years ago. And instead, what they do, and what anyone who's a recursive resolver should do if they're intelligent, is to randomly, 1 in n, add an EDNS0 client subnet to the query. If the server recognizes that and responds, it then automatically adds that server to its list of supported EDNS0 client subnet servers, and thereafter starts doing EDNS0 client subnet full time. That's the way it works.
Yep. So we do some internal study about that.
So do I.
Yeah.
I'm
So
interested in its accuracy.
Yeah. So we do some ISP. We do some DNS. We do actually see that they are actually supporting EDNS0. But unfortunately for us to formally support that, we got to have a formal engagement process with the ISP. Hey, you have to whitelist and then make sure that you support that, and then blah blah blah. So yeah, but this could be one thing that I could feedback into our internal team about how we could improve that process. Yeah, but this moment not yet.
As I said, it's not really the authoritative. The recursives should be offering it anyway. It's really a case of whether the authoritatives are sensitive to it or not. That's what's going on, right? So the trick is, as I said, if the recursives are willing to turn it on by simply probing the authoritatives, your problem's solved. And that's where Google got to because they got sick of maintaining the list.
Yep.
Okay.
Thank you.
Thank you.
Thank you very much. Please, Maz, come on the stage. Yeah, traffic engineering.
Thank you very much. So, someone show me my slide. Yep, that's it. Okay, hi, this is Maz working for IIJ. Looks like I have only 10 minutes, so let me go fast as possible. I'm from IIJ again. We are mostly based on Japan. We maintain our backbone. And we are very conservative about the qualities. We do over-provisioning, and we pretty straightforward. Nothing strange. Yes, we are providing IPv6 services for our customers. We do DNSSEC. You can check our domain name. We are going to adapt RPKI. We do URPF to enforce our customer use proper source IP addresses. Okay, let's go into the topic today. Probably you might hear about over-the-top. It's a contents provider or service provider providing the internet-related service for the end users. They are earning lots of money, yes, but we don't care. We are ISP. We just carrying the IP packets. But we care about volume, traffic, and its trend. As an ISP, we need to upgrade our network to commit our performance, our quality. But as we know, most traffic are not much controllable, right? So we should be flexible and also adjustable to the trend. So let's look into the customer profile. This is an enterprise network. Mostly, they are using the network during the business day. So starting from 9 or 8 in the morning until midnight. It's actually IIJ office network. So we are working hard. And the weekend, yes, the traffic is not that much, but still someone trying something there. So it's a usual corporate traffic. And then broadband. Yes, we providing the broadband services to our customers, residential users, consumers. They use internet for many variety of things like chatting and video streaming or web browsing, or gaming. So during the business day, it looks like people are using at night mostly, but still we are observing traffic during the daytime as well. And then weekend, we have much more traffic than the usual business days. It's a broadband fixed line connectivity. This is our peering traffic toward the IXP. Yes, as you see, we have a narrow peak during lunchtime. That's because of mobile phones. During lunch break, people use mobile phone to check news or have a conversation over the mobile phone, right? That's why we see a narrow peak during the lunchtime. And weekend, of course, as the lunch break is not synchronized, right? So we don't see much narrow peak there. And the usage base. We measure the traffic per user basis and realized that top 10% of broadband users is pushing about 65% of traffic. At the same time, about 90% of incoming traffic is by the top 10% of users. So a little user using the most of the internet resources in our network. For the mobile, yeah, still we have the power users, like top 10% of users using the 50% of the resources. But we have a cap for the mobile services. So that's why probably we don't have that much power users or heavy users on the mobile network at this moment. So what's the usage? 2005, at that time, we have many peer-to-peer traffic in our network. That's why we are observing high port versus high port communication in our network. But year by year, we are seeing more and more HTTP-based or port 80 traffic in our network. And also UDP as well. This is the data from last year. In broadband communication, about 37% HTTP and 443 HTTPS is about 23%. So about half of the traffic is HTTP-related traffic. And also we are seeing the RTMP, video streaming. And for UDP, we are seeing 443 traffic as well. It's a newer wave protocol. And also, it's a little bit strange, but we are seeing the ESP, IPsec traffic, about 7.4%. That's a little bit huge. And the mobile network, yes, over 80% of the traffic is HTTP. And also, we see 1% 443 UDP traffic in our network. So most users are using HTTP-related services, I guess, from CDNs. So Google, Amazon, Facebook, Microsoft, they are a heavy source of port 443. And Akamai, Apple, Limelight, Netflix, we are seeing the heavy port 80 traffic from them. Right? As we are seeing the more and more traffic day by day, year by year, because we have more users and we have more applications, and then we need more bandwidth. So it's time to think about upgrade. In the BGP world, yes, we need to think about peering to have more capacity. And then if we have a multiple peering relationship with other parties, then we can have redundancy there. And also our traffic probably stay some stable status. So, but thinking about peering with CDN, I'm a little bit kind of suspicious feeling. Why? Okay. At the first stage, probably you are receiving the CDN traffic from your upstream as an ISP. So they put the CDN cache in the upstream or somewhere in the internet. Then from there, you are receiving traffic, right? So one day, you decided to have a peering with the CDN to have stability or to have capacity there. In other day, you decided to have a CDN cache in your network, right? This is the model now we are doing in the internet. And one day, you realized there are so many CDN cache or CDN boxes in the internet. And the CDN provider can push traffic from any of these boxes, right? So CDN is getting more capability to distribute their content or their customers' content by deploying cache node in the internet, right? And also they can shift traffic over the earth that we cannot do. So we lose control of traffic. CDNs are getting more. So at this moment, we, ISP, ask CDNs to control the traffic. This is a modern model. So peering and the CDN is a totally different idea. The peering relationship relies on the equal relationship. We tend to prefer adopt a closest exit policy because it's simple, it's scale. But at the same time, we assume the gentle changes of traffic patterns for your peering partners. But it's not true for the peering with the CDN or having the CDN cache in your network. CDN cache enhanced CDN capability, right? We help CDNs to optimize their distribution. In return, then we can reduce its transit cost. That's a model. So thinking about the upgrading and with the capacity of the CDNs, of course, it will be a benefit to our customers. But only CDNs will increase capability of traffic engineering. It's getting more unbalanced. Usually, as a BGP operator, we know outbound traffic control is easier than the incoming traffic control, right? So having the CDN cache or expanding the capacity with the CDN node, it's mutually benefitable, but the risks are different. So it's a not easy way to have a better traffic control. You should be aware of the CDN's traffic engineering, right? But the good thing here, we have a point of contact to negotiate. Unlike P2P, peer-to-peer traffic is not controllable at all. But the CDNs, we have an operator here, so we can ask, we can negotiate. That's a good thing for us. So summary, we don't have control of internet usage. That's true, because end nodes, end host handle it. They can use P2P or CDNs or multi-TCP. It's getting complex. So what can we do? We should keep our network flexible and adjustable. It's a better idea to keep it simple and stupid. And then we can adapt new usage. At this moment, CDN is the major one, but I'm not sure 10 years later. To have a better traffic engineering, we should openly share our operational policy with each other. And APNIC is one of the places to discuss with. That's my talk.
Okay. Thank you to all our speakers. And that was it, our first technical session on network performance.